Hey everyone, welcome back to Brainstorm. This is our Level 2 Algebra walkthrough series. Now, in this video, we're going to go over quadratics. In this first part, we're going to do a bit of a quadratic refresh, as well as we're going to look at solving equations with quadratics in them and different techniques that we can do to do so. So specifically, we're going to look at solving equations with quadratic substitution, as well as completing the square. Alright, but let's, why don't we head on and do our quadratic refresh. So recall that a quadratic is an equation where the highest power of an unknown variable is 2, right? So what I'm saying is if we have some quadratic that looks like x squared plus 3x plus 1, this is just a random quadratic, but a quadratic equation is an equation where the highest value, the highest power on x is actually 2, right? That's why we call it a quadratic equation, right? And our quadratic equations generally have the form ax squared plus bx plus c, right? And a, b, and c, so write this out, a, b, and c are constants. Okay, so if I was to compare the cases here and here, well, in this case, a is equal to 1, b is equal to 3, and then c is whatever's left over, which is just 1, right? So 3 is b, this is the same as 1x squared, so that 1 would be a, and then whatever's left over is the value of c, right? And also remember that when we graph a quadratic, we're going to get a symmetrical shape, which is called a parabola. So if I draw out my axes here, hopefully let's get something straight. Something like that, okay? If I draw a general quadratic might look like, it would look something like this, right? So it's symmetrical down the middle, so I haven't done necessarily a great job, but hopefully you can see that whatever is reflected on the left-hand side will be the same on the right-hand side, okay? But just in general, this is what a quadratic looks like if we were to graph it. So this would be my y-axis, and this would be my x-axis. Now hopefully you remember when we solve quadratics, we usually factorize them into 2 brackets. So for example, I might have the quadratic, I don't know, x plus 3, and x minus 1 is equal to 0. Now how do we solve for this quadratic? Well, what we do is we set each bracket to equal to 0 and then solve them, right? So I would do x plus 3 is equal to 0 and then solve for x. So I would get x is equal to negative 3, moving the 3 over from the left-hand side to the right-hand side. As well as I'll do that for the other bracket as well. So x minus 1 is equal to 0, and therefore x is equal to 1. So I have 2 solutions for x. Have you ever wondered why we set each bracket equal to 0 and then solving separately? Well, it's all a bit of essentially algebraic manipulation. Consider the following equation. Consider if I had the equation a multiplied by b is equal to 0. What does this actually mean? How can this equation ever be true? Well, there's 2 situations where this equation is true. So we've got 2 scenarios. Let's write scenario 1. I'll underline that. The first situation is where the value of a is equal to 0, right? Because something has to be equal to 0 to make the whole, and multiplying by 0 gives 0, and that will make the equation 2. So in scenario 1, if a is equal to 0, then 0 multiplied by b is equal to 0, and we don't actually care about the value of b because we know multiplying it by 0 is going to be equal to 0. In scenario 2, we set b equal to 0, right? So if b is equal to 0, then this will still make the equation true, and that's because a multiplied by 0 still will give 0. So these 2 equations hold, and therefore that is why, because these hold, we're going to be able to prove, well, not necessarily prove, but we can show that quadratics should be, well, we can solve them by setting each bracket equal to 0. Right, and so what I mean to say is that for any general quadratic, if I have x minus p and x minus q equal to 0, where p and q are constants, then let's let a equal to x minus p, and let's just put this in brackets just to make it a bit clearer, and let's let b equal the other bracket, x minus q. Now what we've got here, if we substitute in, a is x minus p, so we'll get a multiplied by x minus q, which was actually b. So a multiplied by b is equal to 0. So what does this mean? Well, because we set each value equal to 0, or before we said this equation is only true if one of these scenarios occur. So in the first scenario, we're saying a is equal to 0 to make this equation hold, right? And so if a is equal to 0, let's go back to scenario 1. Scenario 1, where a is equal to 0, then a is equal to x minus p, and therefore x minus p is equal to 0, right? So this is why we've set one bracket equal to 0, and then we can just rearrange. So x is therefore equal to p, and this is one of our solutions. What about for scenario 2? Scenario 2. Right, and in this case, b is equal to 0, b was equal to x minus q, and also, in our second scenario, we said a was equal to 0, b was equal to 0, and therefore x minus q is also equal to 0, and therefore x is equal to q. And this is our second solution, right? And this is why we can set either or brackets equal to 0 and able to solve for values of x. Next, let's look at solving equations via quadratic substitution. So what does this actually mean? Well, because we know how to solve quadratic equations, sometimes it's actually helpful to use substitution to change equations which actually aren't quadratic into a quadratic equation and solve that equation. Then what we can do is back substitute and get actual solutions for our equation. And I know that's a lot of words, so let's look at an example. So for example, let's assume I had the equation 5x plus the 4 multiplied by the root of x is equal to 1, and I want to solve for x. Now, this is a bit tricky, right? We don't know how to work or solve equations with a root of x, right? And also a x to the power of 1, because this is a bit unfamiliar. So what should we do? Well, one technique that we can do is we can substitute the root of x for a different variable, and let's call that different variable y. It can be called anything. I'm just going to call it y. So let's go let the root of x be equal to y. All right, and now what I can do is I can substitute out the root of x for the value of y. So I'm going to get 5x plus 4. The root of x is y, so 5x plus 4y is equal to 1. But now I've still got this x here, right? And I can't do anything, while this x is still here. So can I manipulate this equation in order to get rid of the x too? In fact, I can. What I can do is I can take the square root, not the square root, but take the square of both sides, and that will get rid of this root here. So what I can do is I can take the square of both sides, and I'll get x is equal to y squared. X is equal to y squared. All right, and I have an x here. So what I can do is I can rewrite this equation. It's 5y squared plus 4y is equal to 1. Okay, and what you can see now is the highest power on one of my y's is 2. I've got an equation in terms of all y's, and therefore this is a quadratic equation. And so now I can solve for this and get a value for y and then back substitute. So how do I do this? 5y squared plus 4y minus 1 is equal to 0. Right, so everything's equal to 0. Now I can either factorize and solve, or I can use a calculator. We're going to use a calculator in our next example, I think. But for now, I'll show you how to do it via factorization if you've forgotten. So what we need to do is multiply 5 and negative 1 together. So the first thing we do is we go 5 times negative 1 is equal to negative 5. And the reason we're doing this is because the coefficient in front of y squared is larger than 1. If you're unsure, you might need to revisit some of my MCAT videos. Now what I'm going to do is I'm going to find a coupled list coupled list of two numbers exactly, which sum to negative 5 and multiply to give 4. I think. Sorry, other way around. We need to find a couple multiple lists which multiply to -5 and sum to 4. Sorry about that. So what can we have? We can have the choice 5 and 1. So 5 and 1 will not multiply to -5, but if I make one of them negative, like if I make 1 negative, then I've got 5 times -1, which does give me -5, and 5 minus 1 does give me 4. So this is actually what we're looking for. And so I'm going to rewrite 4y in terms of 5y and minus y. So if I move over to this side here, I get 5y squared plus 5y minus y minus 1 is equal to 0. Right? And this is the same equation. These equations are exactly the same. I've just broken it up. So what I'm going to do is I'm going to need to factorize twice. So I'm going to just break this equation in half and factorize it to two separate brackets and then see what we can do after. So what's the common factor between these two terms? Well, hopefully you can see that the common factor is indeed 5y. So I'm going to take 5y out. 5y times what gives me 5y squared? Well, 5y times y gives me 5y squared. That gets added with 1 because 5y times 1 is 5y. Then this first section is done. Let's move on to the second section. So we're going to add, and what's the common factor here? Well, it looks like the common factor is actually -1. So we're adding -1 multiplied by -1 times y gives me -y, and -1 times 1 gives me -1. So this would be this would be y added with 1, and that's equal to 0. And so if we look here, we've got y plus 1 and y plus 1 occurring twice, so we can factor that out too. And this is redundant, so we can get rid of that. And so if I make y plus 1 in my first bracket, well, what's left over? What's left over is 5y minus 1, and that's equal to 0. And now we've got our two brackets which we can do solving on. So if I give myself a bit more space, the first solution is y plus 1 is equal to 0, and therefore y is equal to -1. My second solution is 5y minus 1 is equal to 0. So 5y is equal to 1, and therefore y is equal to 1 over 5. Okay, so these are our two solutions, right? But remember, our equation is actually in terms of x. And so I need to use my solutions for y and convert them back into x. So what was our equation that let us do that? Our equation is x is equal to y squared. So I'm going to rewrite this down here. X is equal to y squared. And so I'm going to use this, I'm going to convert it back into x. So our solutions for x are x is equal to -1 squared, as well as x is equal to 1/5 squared. And so my solutions for x are actually 1 and 1 over 25. Okay, but we're not done there. We actually need to check our answers because we're dealing with a square root. So what's our original equation? Our original equation is 5x plus 4 root x is equal to 1. Let's substitute our values of x in to check if they're correct. So our first solution is x is equal to 1. So checking x is equal to 1. So 5 plus 4 is equal to 1. 9 is equal to 1. This is not true. This is not true, therefore we have a contradiction, and therefore x is equal to 1 is not one of our solutions. So x equals 1 is not valid. Let's check 1 over 25 now. So checking x is equal to 1 over 25. So this would be 5 multiplied by 1 over 25, added with 4 multiplied by the root of 1 over 25, and this has to equal 1. Let's check if this holds. We get 5 over 25. 5 over 25 is the same as 1/5. 1/5 added with 4 multiplied by 1 over the root of 25, which is 5, is equal to 1. And so this is the same as 1/5 plus 4/5 is equal to 1. Now 5 over 5 is equal to 1 is true because 5 divided by 5 is 1, and therefore this equation holds. So what that means is, therefore, x is equal to 1 over 25 is our only solution for this equation, right? And so whenever we're dealing with square roots, we usually need to double check our solutions for x. And that's because when we do our conversion from -1, where's my values of y? -1, we actually squared it, right? So we lost that negative sign, right? Because whenever we square a negative number, it becomes positive, right? And that's why we had to do our check to make sure that this holds. All right, let's look at our next example. So, example. Solve 5q to the power of 6 is equal to 9q to the power of 3 plus 18. How are we going to do this? Because what we're dealing with is our highest power is actually q to the power of 6, and we only know how to work with quadratics, right? And so what algebraic techniques could we do in order to solve this? Well, we can see that we've got q to the power of 6 and q to the power of 3, and we know by our exponent rules that q to the power of 6 is equal to q to the power of 2 multiplied by 3, right? And so how do we multiply our powers together? This can be done by doing q to the power of 3 squared, right? And so because we're squaring here, this tells us that we might want to use quadratic substitution. And in fact, that's exactly what we're going to do. And so what I'm going to do is I'm going to set the value of x or y to be equal to the lowest powered degree as possible, right? So in this case, it's q to the power of 3. So I'm going to say, and let's just work with x this time to change things up. So let x equal q to the power of 3. And now I'm going to use my substitution. So wherever I see q to the power of 3, I can substitute in for x. So 5q to the power of 6 is equal to 9x plus 18. But also note that, remember what I said before, q to the power of 6 is equal to q to the power of 3 squared. So q to the power of 3 is x as per this equation here. And so what I'm saying is q to the power of 6 is the same as x squared, right? And so what I can do is I can go 5x squared, because q to the power of 6 is x squared as we've just defined, is equal to 9x plus 18, and lo and behold, we have a quadratic. So let's solve for our quadratic. So if I move everything to the left hand side, I get 5x squared minus 9x minus 18 is equal to 0. So now you can solve by factorization, but I'm going to show you how we can use a calculator to speed up our solving process. Alright, well, what we're going to do here is we're going to take that quadratic, which was 5x squared minus 9x minus 18, and we're going to use our calculators in order to just quickly solve for x. So what we want to do is we want to go to our equation here. So we're going to use, we're going to go to equation, we're going to click execute. And this lets us solve for different types of equations. So we've got the simultaneous equations, we've got polynomials, and then we've got the solver as well. So the solver does algebraic manipulation for you. The polynomials is what we want, because we want to solve a polynomial of degree 2. So we're going to click F2, and we want the degree to be 2, so we click F1. Okay, and then what we need to do is we need to enter values in here in our a, b, and c, which match this form here, right? And so this is just the form ax squared plus bx plus c is equal to 0. So as long as our quadratic is equal to 0, we can just plug in for values of a, b, and c. So in our quadratic, we had 5x squared minus 9x minus 18. And so 5 will be the value of a, so we're going to plug 5 in there, execute. And the value of b is actually negative 9, so we're going to plug that in there too. And enter. And our value of c is whatever's left over, which was negative 18. All right, so we plug that in there, and then what we're going to do is we're going to click F1 to solve our quadratic. And so as you can see, it gives us solutions of x, which is 3 and negative 1.2, right? So our solutions of x are negative, and usually I'll write it in fraction form. So if you hover over that value of x, it will tell you the fraction form. So our values of x are negative 6 over 5 and 3. So what you've just seen is that our solutions for x are x is equal to negative 6 over 5 and x is equal to 3. Now, look here, x is equal to q cubed. But our original equation is in terms of q. So I need to rearrange this to find the value of the single value of q, and then essentially put our x values into that equation. So note that q cubed can be rewritten as in terms of just q by taking the cube root of both sides, right? So what I can do is I can take the cube root of x, and that's equal to the cube root of q cubed, which will cancel out and just give me q, right? And that's just some basic algebraic simplification. So q is equal to the cube root of x. I've got my solutions for x, so I'm going to plug them in. So q is equal to the cube root of -6/5. And also q is equal to the cube root of 3. Now, is this value here, is this a real number? The answer is yes. Even though there's a negative inside the root, because it's a cube root, having a negative number in there can give us valid solutions. Alright, so this is actually a true value, and this is actually a true value as well. And so hopefully if you substitute this back into our original equation here, you'll see that this actually does hold for both values of q. So both values of q are valid in this case. Alright, and let's do one more example. 4x to the power of 4 added with 5 is equal to 9x squared. Solve for x. So in this case we do have a quadratic term, but we've also got a term which is x to the power of 4. However, also note that x to the power of 2 raised to the power of 2 is the same as x to the power of 4. And because we're raising to the power of 2, we're going to use quadratic substitution. In fact, I'll leave this here. So remember what we want to do. We want to substitute for the lowest powered degree here, which is x to the power of 2. And we're just excluding the fact that this can be written, the 5 can be rewritten as 5 multiplied by x to the power of 0. So just forget that. Just the values that are already listed, we want to take x squared in this case. Okay, so we're going to say let x squared equal some variable. Let's call it y. And we're going to start substituting. So 4x to the power of 4 added with 5 is equal to 9y. Alright, and we also need to deal with this x to the power of 4. Note that y squared is equal to x to the power of 2 squared, which is actually x to the power of 4 by our exponent power rules in the first video. And so this can be rewritten as 4y squared plus 5 is equal to 9y. And now if I move everything to the left hand side, I get 4y squared plus 5 minus 9y is equal to 0. And to rewrite it in our general form, this is 4y squared minus 9y plus 5 is equal to 0. And general form is, of course, ax squared plus bx plus c is equal to 0. Right, and 4 matches up with a, negative 9 matches up with b, and 5 matches up with c. Okay? So, what we can do now is solve. Again, I'm just going to put it into a calculator. And in fact, I know the solutions here. The solutions for y are 1 and 5 over 4. Okay, so these are our solutions for y, but our equation is in terms of x. So we need to rearrange for x. So, x squared is equal to y. Let's rewrite this. X squared is equal to y. And so rearranging for y, our value of y is indeed plus or minus the root of x squared. And so y is equal to plus or minus x. Sorry, I have completely rearranged this wrong. So this should actually be taking the root. We'd get x is equal to plus or minus the root of y. Apologies for that mishap. So we've got x in terms of y now, so we can directly plug the value of y back in to get our values of x. So x is therefore equal to, in the first case, plus or minus the root of 1, and so x is equal to plus or minus 1. So this is our first solution, and our second solution is x is equal to plus or minus the root of 5 over 4. And this is our second solution, right? And so this is some examples of how we can use quadratic substitution, and these are generally excellence level questions. Next, we're going to look at something called completing the square. So let's write that out. Completing the square. Okay, and all completing the square is I won't go over the full visual proof, but you have this kind of square which is missing this small little bit of that square. So it's missing that there, right? And so completing the square is what we do, where we want to find this small little block here and essentially complete the square, as we say. And it turns out the value of this little block here can be calculated by b over 2 squared. Okay, but let's actually talk about what completing the square actually is first. So what it is it's a tool which is useful for converting a quadratic of the form ax squared plus bx plus c, and we want to convert that into a new form which is a multiplied by x plus d squared plus e. And hopefully you might even remember from level 1, this is our general form, and this is our vertex form. So completing the square allows us to convert, or allows us to quickly recognize where the vertex of our quadratic is, right? So there's two advantages to having a quadratic in vertex form, right? The first advantage is that, as I've just mentioned, we can easily find the vertex, and the second solution, we can easily find the vertex and therefore the minimum or maximum point, right? Because a quadratic only has one minimum and one maximum. But the other advantage is that we can easily solve for x. We just have to move this over, divide by this, take the root, and then that's pretty much solve for x, right? We just have to subtract off this plus d, right? So I can do that in my head. We can't easily rearrange this. We have to factorize that first, right? And so converting into vertex form is usually something quite nice. The way that we do that is we have to essentially add b over 2 squared to both sides, right? And we won't look at why this is b over 2 squared. I just don't have enough time in this video to do that. But we're going to just take it for granted and just add b over 2 squared. So let's look at an example to make it clear. So our example for this video would be, let's convert x squared plus 6x plus 7 into the form x plus d squared plus e. So the first thing that we do is we don't need to make this equal to 0, but I'm going to, just because it's going to make understanding the process of the computation a little bit easier. So x squared plus 6x plus 7 is equal to 0. And then I'm going to add b over 2 squared to both sides. So x squared plus 6x plus 7 added with, now what's the value of b? Remember our general formula, this is the value of b here. So our value of b is indeed 6. We're adding 6 over 2 squared to both sides. So I'm going to add 6 over 2 squared to the left hand side and the right hand side. Now what actually is 6 over 2 squared? It's 3 squared, which is actually 9, right? And so what we get is x squared plus 6x plus 7 plus 9 is equal to 9. So we've added the 9 on both sides. Why have I done this? Well, it's going to make our lives easier to factorize, but what we want to do is we want to get rid of the 7. So I'm going to subtract the 7 and move it over to the right hand side. So x squared plus 6x plus 9 is equal to 9 minus 7. Simplifying this, x squared plus 6x plus 9 is equal to 2. Okay, now let's factorize this here. So hopefully you can recognize that actually this is what we call a perfect square. And the reason for that is if I try and simplify this, the only two numbers which multiply to 9 and sum to 6 is 3 and 3. So I get x plus 3 squared is equal to 2. right? So this is a perfect square because it's the same root repeated twice. So if I move the 2 over back to the left hand side, I get x plus 3 squared minus 2 is equal to 0. And remember, because I added this equals 0 to our expression, which wasn't needed, I can actually just get rid of that. And so this is now in vertex form because I can rewrite this as x plus d squared a multiplied by x plus d squared plus e, and the value of a is equal to 1, the value of d is equal to 3, and the value of e is equal to negative 2, right? So this is vertex form, right? And we've answered our question there. All right, let's look at our final example for today. Let's write 3x squared plus 13x plus 12 into the form x plus d squared plus e. And also let's determine the coordinates of the minimum point. The minimum point. So there's a lot to take in first. So what we want to do is 2 steps. First, we want to convert into the form, the vertex form, and then determine the coordinates of the minimum point. So how do we do this? Well, this situation is a bit different because my value of x squared has a coefficient of 3 in front of it. So the first thing I'm going to do is just divide by 3 to get rid of that. So I'm going to get x squared plus 13x over 3 added with 12 over 3. This can be simplified more to be x squared plus 13x over 3 plus 4. Now I'm going to set the expression equal to 0. X squared plus 13x over 3 plus 4 is equal to 0. And now I'm going to complete the square by adding b over 2 squared to both sides. So x squared plus 13 over 3x plus 4 added with b over 2 squared. So b over 2 squared is the same as 13. In fact, let's rewrite this separately. So b over 2 squared is that divided by 2, which is the same as multiplying by a half, squared, which is the same as 13 over 6 squared. Alright, so I'm going to remove this here, and we're just going to add 13 over 6 squared onto both sides. Okay, 13 over 6 squared onto both sides. Now I'm going to get rid of this plus 4 here, because we don't want that, we want it on the right hand side. So x squared plus 13 over 3x plus 13 over 6 squared is equal to 13 over 6 squared minus 4. And you might be thinking, why do we want to get rid of this plus 4? Just the reason we're doing that is because with this plus 4, we can't make a perfect square. But if we don't have the plus 4 here, and we're left with just this here, this always gives a perfect square, okay? If we have b over 2 squared with these two, the other coefficients of a and b, we always get a perfect square, and this helps convert to vertex form, right? And so now that we've got this here, I can rewrite this as a perfect square. So the perfect square of this is just x plus 13 over 6 squared. That's equal to 13 over 6 squared minus 4. And then all I do now is I just add this back over to the left hand side. So x plus 13 over 6 squared minus 13 over 6 squared added with 4 is equal to 0. And remember that this is an expression, we actually don't need the equals to 0. Right? And so this, technically speaking, can be vertex form because I can simplify this even further. And I do have a calculator next to me, so I can do that. So I'll go x plus 13 over 6 squared. And then if I go 13 over 6, I square that, and I multiply it by -1, then I add 4, I get negative 25 over 36. I hope I've done that correctly. Okay, so this is my expression here in vertex form. This is my value of A is 1, my value of D is 13 over 6, and my value of E is negative 25 over 36. What's the second part of my question? We want to determine the coordinates of the minimum point. Now look here, this is a positive parabola, right? So if I was to draw a graph, it would look something like, I have no idea where it would be, I guess somewhere here, right? Right, and what that means is that we have one minimum point which is down here somewhere. So because we're in vertex form, it's really easy to actually get this minimum point. The minimum point is going to be at the y-intercept. The y-intercept is given by the value of E. So my value of the y-intercept is negative 25 over 36. And the value of my x-intercept can be found, not x-intercept, sorry, the value where the vertex, the x value of the vertex can be found by setting this bracket equal to 0. So this will just be the opposite of this value, right? So if x plus 13 over 6 was equal to 0, then x is equal to negative 13 over 6. Okay, so negative 13 over 6 is my x value. Right, and this is the coordinates of the vertex. So coords are given here, right? And this is the solution for this example question. Awesome, thanks for watching, guys, and I'll see you guys in the next video, which is about the quadratic equation, or the quadratic formula, as well as the nature of roots. Cheers.